Okay, so it's time to start a new unit, and I feel like I'm gonna say this every unit that we start from here on out, but this is a really, really important unit, and us are the ones that are going to be coming up. What we've been doing so far is getting ready to do college level chemistry. And now that we're going to get into kinetics and equilibrium, these are the big subjects. These are the ones that you know, that I don't know, tell the difference between, just high school chemistry and college chemistry. And they're actually some of my favorite units. The problems, are things that if you work hard, you'll have no trouble understanding them, yet they're challenging, so they really push your mind, and I think you'll really enjoy it. So let's start with what does kinetics mean? Because that's what this whole next unit is going to be about. And you can see there on your paper that kinetics is the study of the rates of reactions and how fast they're going to occur. You know, in our class and if you're experiencing chemistry, the reactions you've been looking at have all been the type of reactions that boom, just happen, boom, just happen. We mix our chemicals together and boom, we get product. But not all reactions are like that, thank goodness. Otherwise, your car would rust the second you drove it off the lot, or a marble statue would disintegrate immediately upon being put out into the elements. Some reactions take longer than others, and that's really what we're going to be looking at is how fast reactions take place. And it can be a really, really interesting conversation because there's a lot of application for it. Now, you might remember from last year, this next part here, the rates, the things that determine the rate or the things that affect the rate of a reaction. We talked so briefly about it last year, but some of them are common sense. Like, for example, if you increase the temperature in a reaction vessel, most of the time the rate of the reaction is going to increase. And I say most of the time because there's some weird exceptions, but increasing the temperature is going to make your particles move faster. And that is something that we are going to be looking at and focusing on as time goes on. That's going to be the subject for a later lesson. We're going to talk about catalysts. You probably already know from English class and from biology class that a catalyst is something that speeds up a reaction. So talking about it in kinetics is the right place to talk about it. And we'll talk about catalysts for sure. The one that we're going to spend the most time on is this first one, concentration of reactants. If we increase how much reactant we have, we are more likely to get a collision, and thus the rate of the reaction is going to speed up. And we're going to spend a lot of time talking about that one. This last one here, number 4, actually, we're going to talk about it just right now because it's a pretty easy concept, and it's one that doesn't really need a lot of discussion, and that is the surface area of a solid. This is the idea that if you put like rock salt, which are huge chunks of salt, in water, you will get it to dissolve, or if it was something that was actually reacting with a liquid reactant, you would get them to react. But remember, the reaction can only take place as the particles hit the surface of the solid that's being reacted. So if you have a big chunk like that, then you're going to have a limited surface area. But if you take that big chunk and you divide it into 4 pieces, please forgive my artwork. So that's a dissected piece. Does that look like it? I hope so. You see that you have much more surface area. Now, not only do we have the outer parts of this molecule, but we also have these inner parts now that can come into contact with the liquid and dissolve. And so by increasing the surface area, you increase the rate of the reaction. And that's a factor that's important. You might think about our mortar and pestle. Sometimes we grind up our solids to make them more accessible for reaction. And so that's really what we're going to be looking at. And like I said, we're going to spend the vast majority of our time right here on concentrations of reactants. That's where we're going to get started today. But we will come back and revisit these other 2 as well. Okay, so let's get into the rates of reaction stuff. If you take a look on your paper, you have some beakers, and this is supposed to indicate a reaction taking place. So we are going to be dealing with 10 moles of our mixture here, and we are going to use a dot, a little molecule looking circle, to represent a mole. Okay, so at the first one, we have 10 moles of A. So let's go ahead and draw 10 little circles inside of our beaker. Okay, and no moles of B. Okay, so we're going to use the color red for A. And you can use whatever you want. You can make it a lighter circle and a darker circle, whatever, if you just have a pencil on your hand right now. So for the next one, so this was at 0 minutes. There's no reaction yet. So you see only A, only our reactant is there. Now as time starts to go on, so at 20 minutes, it's telling us that our reactant A has gone down to 6 moles. So I'm only going to draw 6 little red dots. And now we've made some product because this reaction has started to take place. So we're going to go ahead and I'm going to use blue for mine. I'm going to do 4 moles of product. So you can see the reaction has started to take place. Okay, we're going to go back to red. And at 40 minutes, I'm now down to 3 moles of A. So I'll use 3 little red circles. And then I'll go back to blue and I'll use 7. Is that 7? 7. Okay. And then I'm going to put 8 blues on this one. Okay. And then I'm going to go back to red. And 1, 2. Okay. So this is just showing you some data, essentially, as this thing goes from 0, 20 to 40 to 60 minutes. First of all, first question is looking at this, has this reaction finished? Well, we can't really tell. I mean, we still have some reactant left over, but we're going to talk in the next unit about how that's a possibility, that we could end up with some reactant. So it's kind of hard to tell that. But what we can tell is that as this reaction proceeded, the reaction slowed down. And if you don't see that right away, take a look. Let's focus on A. So we started at 10 and we went down to 6 moles of A. So we used 4 moles of A up that first set. If you look at the second interval, we go from 6 to 3. So we only used 3 moles of A. If you look at the next interval, we went from 3 to 1. So we only used 1. So you can see that as the reaction's going on, we are actually decreasing the rate of this reaction. It's slowing down. Now, why would that be? If you look at the pictures, hopefully it becomes obvious to you as we start to look at this. If you look in this first beaker here, you have tons of A. There's lots of red particles to bump into each other, and in order to react, they must collide. Okay, so you have tons of A to react with each other and to form product. As you go to this second beaker, you still have a decent amount of A to be able to react and become B. As you get here, it's getting harder to find another red molecule to react with. And so you're naturally going to see a slowing down because you don't have as much reactant. Remember we said the more reactant you have, the faster the reaction will be going. So here we had the most reactant and it's going the fastest. Towards the end is where it's going to start to slow down. And as we get to this beaker, you see it's going much slower because in order to react, these 2 red particles would need to find each other. And they're getting further and further away from each other. Now we can actually calculate. I used these numbers, and we'll talk about these numbers. They're not really the calculation, but we can actually calculate the rate of the reaction, how much we're losing or gaining at any given time. So let's go ahead and first of all, I'm going to be using this term a lot, so let's make sure you understand. So when I say the rate of a reaction, it's a measurement of how quickly the reactants are being used up, or it's a measurement of how quickly the products are being produced. So this is really 2 parts to this. How quickly the reactants are being used up, sorry, that should be in there. And then it's also a measurement of how quickly the products are being produced. We use up reactants, we produce products. And you can see there's 2 reactions here, 2 equations here. The only difference, and you can see as we start to look at this, is that one is for products which appear, that's why it's called appearance of products, and one is for the disappearance of reactants. Okay, now take a look at these equations. It's a pretty straightforward equation. It's just the change in moles or molarity. So we can do moles or molarity of your product. Okay, so B is indicating product over change in time. And then the rate of disappearance has change in moles, this time of A, because that's your reactant, over change in time. But please notice this little guy right here. That is a negative sign. And the reason for that is that reaction rates are always positive. Please write it down. I'm writing it too for a reason. Okay, they're always positive. So if you're trying to calculate the rate of disappearance by this equation, if you plugged in change in moles over change in time, you would have gotten a negative number, and that is not okay. Reaction rates should always be positive. Okay, so I'll show you how this works in just a second with a problem, but it's a pretty straightforward equation. It's a pretty simple equation to use. Just real fast before we move on to an example of the rates of the reaction, There's actually two different types of rates of reaction. One's called an instantaneous rate of reaction, and the other one's called the average rate of reaction. I do want you to be familiar with both terms, but this is the one that we are going to use. Okay, that's the one we're going to calculate. Instantaneous rates of reactions are measured at a specific time during the reaction. So at a very specific time, you are figuring out how fast the reaction is going. For average rates of reaction, you're doing it over a time interval. So maybe for the instantaneous, you're trying to figure out the rate, oops, you're trying to figure out the rate of your reaction. Oh, man. Sorry about that. So let's say you're trying to figure out the rate of your reaction at, say, 15 seconds. Okay, that would be an instantaneous rate. Maybe you're trying to find the average rate from 10 to 20 seconds. Okay, that's an interval. Okay, we're going to be doing the interval types because the instantaneous ones, really you have to graph and find the slope at a specific point on the graph. And it's really hard on the AP test for them to ask those kinds of questions. So typically we're going to see average rates of reactions type problems. Okay, but I do want you to be familiar with that term. All right, so here's the same problem that we were doing before, except that I modified the values a little bit. If you look here, instead of 10 total, we're using 1 total. And I'm going to show you how these calculations work. And again, I think you'll agree with me once we're done with this problem that it's pretty straightforward, simple equation. Okay, so remember, our reaction rate is going to be equal to our change in moles over change in time. It's possible that it may need a negative in the equation if it's for the disappearance equation, because you can never have a negative reaction rate. So for this first one, it wants us to find the rate of the reaction of the product B. So we're doing product. So we get to use the positive version of the equation for the time interval of 0 to 20 minutes. 0 to 20 minutes. So we are going to be doing change in moles over change in time. Okay, our change in moles. So the time interval is from 0 to 20 minutes. So look only at B. If you take a look at B, you have 0.4 moles. And at this B, we have 0. So 0.4 minus 0 over change in time. So 20 minutes to 0 minutes. Okay, so 0.4 minus 0 and 20 minus 0. And you end up, if you calculate that, getting 0.020. Now the unit's really important, and if you look, it should be very obvious. Our top value was a mole value. Our bottom value was in minutes. So our unit is going to be moles per minute. And again, we could have used molarity as well if they had given us that, but they gave us moles, so moles per minute. Okay, so that's the first one. Now take a look at the second one. I've kind of written over it. I apologize. So same equation. Okay, we're going to do change in time, or change in moles over change in time, this time from 20 to 40. So, and this again is a B. So we're going to do 0.7 minus 0.4 divided by 40 minus 20. And when we do that, we get a new rate of 0.015 moles per minute. So as time went on, the new rate of the reaction during that interval of 40 to 20 is now down to 0.015. Notice I said down. The first time interval, we had a much faster rate than in the second time interval, because like we discussed before, the rate of the reaction is going to slow down as the reaction proceeds. All right, next one, 40 to 60. I just covered my stuff up. 40 to 60. So 40 to 60, we're going to have 0.8 minus 0.7. Remember, we're still working with B. And then 60 minus 40. And when you calculate that out, you're going to get 0.005 moles per minute. Okay. Notice again, we slowed down again. All right, and then this last one, they want it for the entire interval. So these ones showed us the interval slowing down. This one's going to be for the whole time span. So it's not really useful, I guess, because it's going to be an average of something as it slowed down. But it's still, I guess, information. So at 60 seconds, we had 0.8. We're going to subtract that from 0 because at 0 minutes we had 0 product. And then 60 minus 0. And you end up with an average for that whole span of 0.013 moles per minute. Okay. Now, again, I'd prefer to look at this data or those equations because those ones are showing you it as it slows down. Now, for E, it says the rate of the reaction for A at the time interval of 0 to 60 minutes. Okay, now notice this time it says A. Let me switch my pen since I changed to the other one. So this is reactance. Okay, that means that it's changing, it's disappearing, and so we're going to have to use that negative version of the equation. Negative change in moles, sorry about that, that gets flip-flopped, over change in time. And I can use the information I have about A. So at 60, it's 0.2 moles of A, and at 0, it was 1 mole. So we're going to do negative 0.2 minus 1 over 60 minus 0. And when we do that, we get 0.013 moles per minute. Notice positive value. Always reaction rate should be positive. Now, if you notice, these two are the same. The reason for that, and it doesn't always work out that way, but it's saying that the rate of disappearance of A was 0.013 moles for every minute, and the rate of appearance of B was 0.013 moles in every minute. And the reason for that is that the ratio between your A and your B in this example was 1 to 1. If the ratio wasn't 1 to 1, that would not work out that way. Okay, so definitely be careful of that. All right, so one of the things I'm going to have you do before next class period is I want you to try this problem. Now, it's very similar to the other one. You are not going to be worrying about this value right here because they have all your data over here. And essentially, you're going to figure out the average disappearance for each of the time intervals. So you're going to be doing a calculation for 0 to 100, for 100 to 200, and for 200 to 300. Okay, so I want you to go ahead and do that. The other thing I want to show you, though, is that there's one other type of problem. And these problems are actually super, super easy if you see these problems, because it's really just a quick little mole-to-mole conversion. Notice they've given us the balanced equation, and they've told us the rate of disappearance for the H2 is 1.3 times 10 to the negative fourth. And notice the unit, moles per liter per second, which is the same thing as saying molarity per second. Okay, moles per liter per second. And they want to know what the rate of appearance of NH3 is going to end up being. Okay, so what you're going to do is you are going to take your given, which is 1.3 times 10 to the negative fourth. Now write your unit out. It's moles per liter per second, and it's of H2. Okay, since we have the equation and we know one of the rates, we can figure out the rate for everything else because it's all just related to those mole values. So I'm going to put down here at the bottom, I need to get rid of moles of H2. And I need to convert into moles of the one that I am trying to find, which is NH3. Okay, so see how moles of H2 is going to cancel? I'm going to plug in my coefficients, right? That's always how we do a mole-to-mole step. So a 3 and a 2. And then I'm going to plug that in my calculator. And when I do, I get 8.7 times 10 to the negative fifth. Now, unit-wise, look what we have left here. We have moles of NH3, and then we never touched that. So our unit is going to be moles per liter per second of NH3. So again, when given rate of something, either appearance or disappearance, you can figure out everything else just using a quick mole-to-mole step. It's actually wonderful and easy and fantastic. All right, so go ahead and work on that. You have some problems to do, and we will reconvene.